Imagine a discovery so profound, so revolutionary, it shifts the very foundations of how we understand the world. It's hailed as a triumph of human ingenuity, published in prestigious journals, and taught in universities. But what if years later, someone tries to repeat it? What if they follow the instructions perfectly, meticulously, only to find nothing? The results simply aren't there. Was the original finding a fluke, a mistake, or perhaps something far more unsettling? This isn't just a hypothetical thought experiment. It's a chilling reality that has shaken science to its core, leaving us to wonder what truly counts as a scientific truth. At the heart of all scientific endeavor lies a simple yet powerful principle: repeatability. If an experiment works once, it should work again, anywhere in the world under the same conditions. It's the bedrock of trust, the ultimate filter that separates genuine insights from mere anomalies. Without it, how can we truly distinguish a fundamental truth about the universe from a clever illusion, a stroke of luck, or even something more deceptive? This principle isn't just a dry academic rule, it's the very heartbeat of progress. Think about some of the most famous breakthroughs in history: Newton's laws of motion, Einstein's theory of relativity, the discovery of DNA. Each of these wasn't just a singular moment of genius. They were theories and observations that could be tested, verified, and yes, repeated, time and time again. These were truths that stood up to scrutiny, that transcended individual labs or specific conditions. But what happens when that bedrock begins to crumble? Let's journey back to the late 1980s, to a story that captivated the scientific world and beyond. Two esteemed electrochemists, Martin Fleischmann and Stanley Pons, announced something incredible. They claimed to have achieved cold fusion, a nuclear reaction happening at room temperature, releasing vast amounts of energy. If true, it would solve the world's energy crisis overnight. The potential was staggering, the implications revolutionary. The media went wild, the public was ecstatic, and even governments started pouring money into research. It promised a future of limitless clean energy. The initial reports were sensational. Fleischmann and Pons described a tabletop experiment involving heavy water, a palladium electrode, and an electric current. They claimed to have observed excess heat, far more than could be explained by chemical reactions alone, along with traces of nuclear byproducts like tritium and neutrons. They even presented preliminary data, fueling the excitement. It seemed too good to be true. And often, things that seem too good to be true are. The scientific community was predictably divided. On one hand, the implications were too enormous to ignore. On the other, the claims were so extraordinary they demanded extraordinary proof. Researchers around the globe immediately scrambled to replicate the experiment. Labs at MIT, Caltech, and even across international borders initiated their own setups, hoping to confirm this miracle breakthrough. The race was on, not just for scientific glory, but for humanity's future. The world held its breath. But, as days turned into weeks, and weeks into months, a disturbing pattern began to emerge. Most research teams reported failure. Despite meticulously following Fleischmann and Pons's published methods, they couldn't reproduce the excess heat, let alone the nuclear byproducts. Some reported fleeting, ambiguous signals, but nothing consistent, nothing definitive. The initial euphoria began to curdle into doubt, then suspicion. The silence from the successful replications was deafening. The scientific method, in its relentless pursuit of truth, is often a brutal crucible. It demands that extraordinary claims be met with extraordinary evidence, and that evidence, crucially, must be independently verifiable. Without that, even the most compelling story, backed by impressive credentials, remains just that, a story. The cold fusion case quickly became a prime example of this unforgiving demand for proof. Critics began to dissect the original claims. Questions arose about the purity of the palladium, the sensitivity of the instruments, even the interpretation of the data. Were Fleischmann and Pons seeing what they wanted to see? Were subtle environmental factors playing a role they hadn't accounted for? The pressure mounted, and the public spectacle began to overshadow the actual science. It was turning into a very public, very painful drama. Here's where it gets complicated. Fleischmann and Pons, and a handful of other researchers, continued to insist their findings were real. They argued that their specific conditions were incredibly hard to replicate, perhaps requiring a rare combination of material properties or experimental finesse. They suggested that mainstream science was simply too close-minded, too quick to dismiss revolutionary ideas that challenged established paradigms. This introduced a fascinating twist. What if the problem wasn't their results, but everyone else's inability to achieve them? This raises a crucial philosophical question for science. How many failed replications does it take to invalidate an initial finding? Is it 1, 2, 100? And what if the original experimenters genuinely believed in their results? The human element, the powerful psychological drive to confirm one's own groundbreaking work, can be a potent force, sometimes blinding us to alternative explanations or even subtle errors. It's a delicate balance between conviction and scientific rigor. So, was cold fusion just a really good story, or was it something more? The consensus among the vast majority of physicists and chemists today is that the initial claims of cold fusion were not substantiated. No reliable, repeatable evidence of nuclear reactions at room temperature has ever emerged. The field, once heralded as a beacon of hope, largely faded from mainstream scientific pursuit. It became a cautionary tale, a scar on the collective memory of science. But here's the truly strange, counterintuitive twist. While mainstream science declared cold fusion a dead end, a small, dedicated community of researchers never gave up. They rebranded it as low-energy nuclear reactions, or LENR, and continued their work, often in obscurity, funded by private sources rather than government grants. They claimed to find some anomalous results, some hints of excess heat, even if not the dramatic nuclear yields initially promised. They believed there was a subtle, elusive phenomenon at play that the broader scientific community had prematurely dismissed. This enduring, albeit fringe pursuit forces us to confront a difficult question. Can a scientific concept be mostly false, but still contain a kernel of truth? Is it possible that the initial, grand claims were indeed overblown, but that a very subtle, hard-to-replicate phenomenon was present all along? Or is this just a classic example of confirmation bias, where proponents only see what supports their already deeply held belief, ignoring all evidence to the contrary? The cold fusion saga highlights the sheer human drama inherent in science. It's not just about sterile facts and figures. It's about ambition, ego, peer pressure, and the agonizing process of self-correction. It reminds us that scientists are human, susceptible to error, misinterpretation, and the powerful allure of a paradigm-shifting discovery. The search for truth is messy, fraught with missteps, and sometimes even blind alleys. The lesson from cold fusion is profound. Repeatability isn't merely a preference, it's a non-negotiable requirement. It's the ultimate gatekeeper. Without it, even the most thrilling announcement, the most promising theory, remains outside the realm of established scientific knowledge. It might be an interesting hypothesis, a curious observation, but it cannot be called a scientific fact. So, what is the enduring legacy of cold fusion? It stands as a stark reminder of the self-correcting nature of science, even when that correction is painful and public. It demonstrated the power of collective skepticism, the importance of open peer review, and the essential role of independent verification. It reminds us that science isn't about individual genius alone, but about a global, collaborative, and often argumentative pursuit of objective reality. It also highlights the fine line between pioneering genius and outright error. For every accepted revolution like quantum mechanics or genetic engineering, there are dozens, if not hundreds, of promising leads that ultimately fade, unable to withstand the rigorous test of repeatability. This isn't a failure of science. It's the very mechanism that makes science so robust and trustworthy in the long run. The cold fusion affair wasn't just a story about a failed experiment. It was a defining moment for the scientific community, forcing it to reaffirm its fundamental values. It solidified the understanding that a scientific truth isn't determined by how exciting it is or how much it promises, but by its ability to be independently confirmed, consistently, universally. So, when an experiment can't be repeated, was it still science, or just a really good story? The answer, unequivocally, is that if it cannot be replicated, it remains at best a compelling anecdote. It might spark curiosity, inspire further investigation, and even reveal the limits of our current understanding. But it does not and cannot form part of the established body of scientific knowledge. Repeatability is the key that unlocks truth. The journey of science is not always a straight line. It's filled with detours, dead ends, and moments of profound reevaluation. But it's precisely this commitment to rigorous testing, to the unforgiving demand for replication, that allows science to self-correct, to weed out the false claims, and to ultimately build a more accurate and reliable understanding of the cosmos and our place within it. It's a continuous, often messy, but ultimately triumphant process.